Hi. This year I was hoping to bring you a nice video about this thin client from IBM, but I haven't been able to get these thin clients to work or boot FreeDOS, so that's out of the picture for this year. So instead, for Doscember, I'm going to show you the progress I've made on my MS-DOS platform game Bob's Fury. You can see it running in the background here. Last time I spoke about it, I was in the middle of implementing CGA and VGA graphics, and that is complete. So the first thing we're going to take a look at is how well it works now that I've got it working.
I've compiled a special edition of the game, primarily for XT systems with a low amount of memory. The executable only contains support for CGA graphics and PC speaker sound, which saves about 20k right off the bat. I've tested this on 86 box configured as a 4.77 MHz PC with 256k of memory. With new graphics code, it mostly achieves full speed, with some slowdown where there is a particularly busy screen. I also tried out the standard release, which runs quite well on a similar machine, only very slightly slower. However, the extra hardware support comes at the cost of memory, so 256k is a little bit of a squeeze. It's probably best to have at least 320k. Out of interest, I configured 86 box for a VGA card in the PC. This actually performs better than CGA does, running the game noticeably faster, although busy screens still suffer from slowdown. With 86 box set up as a 386SX running at 20 MHz, the game runs at full speed with plenty of cycles to spare. The main improvement over the BGI version here is essentially less flicker in the graphics and faster responses. The new version also essentially eliminates slowdown at this speed of processor.
The new graphics libraries for CGA and VGA graphics means Bob's Fury runs quite well on XT systems now, although there is a little bit of slowdown on some of the busier screens. That's not the only work I've been doing, however. I've been working on making the high resolution mode work as well, and that's usually supported with something called VESA. Let's take a quick look at how it works before I demonstrate it working.
I've selected 640 by 400 for the high resolution mode, as it's a multiple of the base resolution for the game. This makes it easier to keep all the visual elements the same relative size across all the supported graphics modes. This will require an SVGA card and access to a significant amount of video RAM, so bank switching will be required to access the 250k needed. The problem with writing code for SVGA cards is that there is significant variety among them, which is why DOS games supporting them sometimes had spotty support. I just don't have the resources to make code for every type of card and test them all. Fortunately for me, the VESA organisation made a standard programming interface to make such things much easier. This standard is known as the VESA BIOS extension, as many cards have it integrated into their ROM. There are some SVGA cards that do not have this extension in the ROM. Support can also be added by using a DOS TSR, such as UniVBA. The first step in using the VESA graphics system is to check if the desired resolution is supported by the card. Essentially, you can ask the BIOS extension if it supports a particular mode, and it returns the data structure on the left. It provides information about accessing the video RAM. This is done with either 1 or 2 windows. These windows provide access to a portion of video RAM at a time, and can be moved to a number of fixed locations. The distance between these points is called the granularity. To begin drawing, we need to know where to put the image data. The pixels are arranged in memory the same way as they are in VGA mode 13 hex, except with 640 pixels per row. However, the windowing system complicates things, as we need to determine where in video RAM the window should be placed, and the position within the window that a pixel resides. I do that by determining the VRAM offset of the pixel, and use that to calculate the granule to move the window to, and the offset within it. The VRAM offset can be larger than a 16-bit number, but with a bit of clever math, I was able to do everything in 16-bit words. Having worked out where a pixel is, it's fairly straightforward to draw one. Simply write the colour byte at the correct location. This can require moving the window, but this has a cost, so that's only done if it's required. Unfortunately, other drawing primitives are a bit more complicated. The filled box is a good example of this extra work. We have to keep in mind that anything we draw can and likely will cross window boundaries. In my code, filled boxes are drawn a row of pixels at a time. There are two conditions where extra code is needed. If the window ends in the middle of the current row, special code is invoked to properly draw until the end of the window. Move the window, and then complete the row of pixels. If the window ends between rows, the window needs to be moved and offsets adjusted between row drawing loops. The same idea applies to other primitives such as images and lines, although the implementation differs, so I won't go into detail on how they work. The good news is that I've already finished the VESA code and integrated it into the game. Support for most SVGA cards seems to be good, although I am only able to test a variety of them under emulation in 86box. They mostly seem to have the same memory configuration with a 64K window and granularity. I have been able to test against a card with different window and granularity values, and so far they have worked fine. The only configuration that doesn't work so far are cards using two windows that have one as read-only and the other as write-only. Fortunately, these seem to be in the minority. So let's now take a look at the graphics code in action. I configured 86box to have a Trident 8900D card with the 386SX. I didn't expect this to run as well as it does. The BGI needed a 486 or better to achieve results on the same level. The game's internal benchmark indicates that the new code is near 6 times faster than the BGI in drawing images using copyput. Certainly quite a large improvement. Given the microbyte machine has a Trident chip, I thought I'd see if the updated game works with VESA graphics. The video BIOS does not have the VESA BIOS extension, so I had to run a TSR to get it to work. Initially, it ran slowly, looking like about half the speed. Looking at the slowness, I thought that perhaps the cause wasn't the graphics code, but rather the timing code. If I disable doubling the pit speed, the game then runs at the correct speed. I suspect the TSR somehow affects how it operates, as other graphics modes run at the correct speed with it enabled. I also ran it on my Pentium machine, which is honestly a bit overkill in terms of performance, but it does confirm that the game runs correctly on its S3 graphic card. In this case, no TSR is needed, and the game works fine with the normal settings.
I'm really pleased that I got the high resolution mode working on my game, but also on this old 386SX system. The old BGI version needed roughly a 486 or Pentium to get it working anywhere near as well. So that's really quite a boost in the amount of hardware support that we've got there. The only graphics mode I've got left to do is EGA 640 by 200 with 16 colours, and that graphics mode is a lot more complicated to program. I'll be attempting to do that probably sometime in the new year when I have time. Fortunately, I've had some information given to me about how to program for it by Jim Leonard, who found some books online for me to read. So hopefully that will be enough to get it working. But it is quite a challenge, and we'll see how we go. Anyhow, that's all I've got for today on this Doscember, whatever day of the month it is. I hope you enjoyed watching the video. Thanks for watching, and I'll catch you next time.